In this lecture, we'll be deriving the Young's equation for the case of partial wetting. Now, in the previous lecture, we had shown that if you have partial wetting, there is a quantity called the spreading parameter S, which is less than 0. Further, in the previous lecture, we had also derived this Young's equation using a force balance approach, which in other words, this Young's equation tells us the relationship between the three interfacial energies that are possible, that are present in a partial wetting scenario. Now, the goal of the lecture now is to understand the relationship between these three energies and how they are related to the contact angle. And to do this, I'll consider a simple situation where we have a sessile drop sitting on a solid surface. And to keep matters simple, I will also consider a situation where gravity is not important. So therefore, there is only one energy, which is the surface energy, that has to be minimized. And as you know, if you only have surface tension or the surface energy that has to be minimized, then the shape of the droplet would be part of a sphere, because as you know, a sphere has the lowest surface area for a given volume. So you would expect that in the absence of gravity, the droplets would take a shape of a sphere. Now, in addition, along with this surface, we also have an additional constraint at the so-called three-phase contact line. This three-phase contact line is also shown on the right image, the three-dimensional image in yellow, where this is basically a one-dimensional object because it's basically a line, and this line is the line of intersection of two surfaces, the surface of the liquid and the vapor and the surface of the solid in the vapor. That's just a solid surface. Okay. Now, at this contact line, we will basically have a contact angle as well, meaning the surface will meet, the liquid vapor surface will meet the solid with a prescribed angle. Now, conventionally, the contact angle is usually taken to be in the liquid. So in this case, I've called the contact angle as theta E, because we are in thermodynamic equilibrium. This angle theta E is sometimes also referred to as the Young's angle, which is with the subscript y instead of E, theta y. Some people also refer to the static angle because thermodynamic equilibrium is possible when you are in a static situation. So you can also call it theta S. So the goal is to understand the relationship between this contact angle theta E and the three interfacial energies that are present in the problem. Unlike the force balance approach, here we'll do an energy minimization approach, taking advantage of the fact that the surface of the droplet is actually part of a sphere. So it's really a spherical cap that is sitting on the surface of the solid. So let us begin by laying down the basic assumptions that we are going to employ. So we have S is less than 0, that is partial wetting. And I've defined it to be a part of a sphere, therefore the radius of that sphere is R. R is radius of the sphere. Theta E, this is the contact angle. H is the height of the droplet. And RC is the wetting radius. Okay. So this theta E can also have alternatives as theta Y or theta S. I'll stick to theta E for now. Okay. So let's write down the goal of the lecture. The goal is to understand how the contact angle theta E is related to the three interfacial tensions in the system. Now, theta is an equilibrium property, so therefore we can use energy minimization. Okay, so let's write down the total energy in the system. The total, or rather in this case, it's only the surface energy. The total surface energy of the sessile drop is given by the sum of all interfacial energies. And what are them? They are basically I'll put a superscript T. It will become clear why I'm calling that T. No, maybe we'll just ignore that for now. I'll directly write a simplification. So the total surface energy would be A solid liquid times gamma solid liquid. That's the surface energy of the solid liquid, and gamma SL is the surface energy per unit area of the solid liquid interface. Then we have solid, let's call this gas or vapor, and gamma solid vapor. And finally we have a liquid vapor and gamma liquid vapor. These are the three surface energies that we have, right? Now we slightly shorthand notation for all of them. Gamma liquid vapor is just the surface tension of the liquid, and a gamma of the solid gas interface we'll just call it as SL, but then solid vapor we'll just call it as gamma S. Okay. Now note that the solid vapor surface is not the total solid vapor surface, because if you notice here, so this is my solid vapor surface, but then a part of the surface is not available to the vapor. It is exposed to the liquid instead. And what is the part of the surface? For example, if this is RC, then this region here that I'm shading now, this is basically, this region is the solid liquid. So I can write down the total solid vapor that I'm interested in is actually A total minus A solid liquid. A total is the entire surface area of the solid minus the whole that basically that's present on the solid, which is now covered by a liquid, right? Now this part here, A total, this part that is A total, it provides just a constant contribution to the total energy and can be neglected. What am I trying to state here? If you notice that the total energy, we are not interested in absolute energies. Remember, we are interested in, when we do an energy minimization, we are interested in changes in the energy that's what matters to us. And any constant value gets nullified because its contribution does not matter when it comes to changes, because the solid surface remains fixed. So we can basically ignore this contribution completely, and therefore we now have the energy, surface energy, functional. It's a functional of the area A, and this is nothing but A solid liquid times gamma solid liquid plus a solid vapor, and solid vapor contribution is nothing but minus ASL times gamma S plus a liquid vapor times gamma. That's what we have for the various surface energies, right? And we can do some simplification here. This is nothing but a gamma times a liquid vapor, that's the first part, plus a solid liquid times gamma SL minus gamma S. That's the expression of the energy, surface energy that we have in the problem, right? Now, what do we want to really do? What we want to do is the following. The problem statement is minimize E surface of A subject to a fixed drop volume. Let's call this drop volume as V. So we want to minimize the surface energy subject to a drop of volume V. How do we do this? Now we have already written down this expression for the surface energies. Okay. Now let's write down the expression for the volume. So let's return to the picture that we have here. So because it's a spherical cap, this is a spherical cap here. I can use geometry to write down the expressions for all these quantities that are shown on the figure. That is, I can write down the expression for the small h, RC, and the volume, the surface area, the wetting area, all of this in terms of the radius of the spherical cap, capital R, and the contact angle theta E. So let's write down each one of them. The volume of the spherical cap, this is, let's say it's V, it's a function of the radius of the spherical cap and the angle theta. This is nothing but pi by 6h into 3r square plus h square, 3rc square plus h square, where these quantities h, which is again a function of radius and theta E, this is nothing but r into 1 minus cos of theta E, and small r is again a function of r and theta E, this is r sine theta E. So we can substitute both of this into the expression for the volume, and this volume essentially becomes pi by 3 r cube times 1 minus cos theta E whole square times 2 plus cos theta E. That's the expression for the volume, right? So the next one is the surface area. The surface area of the cap. What is the surface area of the cap? That is the liquid vapor interface. Okay. And this quantity is just 2 pi RH. That's 2 pi r square 1 minus cos of theta E. The wetted area of the solid, that is basically the area of the where the drop meets the solid, the liquid meets the solid, and this we had called it as a solid liquid in our expression. This quantity is pi RC square, right? And I should call this as C, sorry, please correct this. This is C RC square, and pi RC square is nothing but pi r square sine square theta E. right? So now we have the surface areas, we have the volume, and we have the expression for the energy functional. So I can substitute the expression for the areas into the energy functional and get the expression for the energy. And the idea is we look at variations in the energy. So variations of energy can come from two reasons. One is you could have variations in the radius capital R, or you could have variations in the contact angle. So what do we minimize with the variation in the energy? We want to take the variation of the energy and set it to 0, and we want to do the same thing where we have a volume constraint. So we are not directly taking the approach that we had done in the previous lectures, where we define an auxiliary function in terms of a Lagrange multiplier, and then use energy minimization on this auxiliary function. We are not taking that route. We are directly taking a different route, because here we know the shape of the droplet, we know the volume of the droplet, surface area, so it makes the calculation easier. And hopefully this also makes the whole process a little transparent. So the total energy of the system this is energy functional. This is what we wrote down earlier: liquid vapor times gamma plus solid liquid times gamma SL minus gamma S. And this quantity, if we substitute all these expressions, what we have now is pi r square sine square theta times gamma SL minus gamma S plus 2 pi r square into 1 minus cos theta times gamma. Okay, so gamma liquid vapor is 2 pi r square into 1 minus cos theta E. So I should call this as E here, sorry. And then solid liquid is just pi r square sine square theta E. So this is E surface of E, right? Let's label this equation. Let's label this equation as 1. Okay. Now the variation in energy is simply written as, let's call it as dE surface of A. This dE is nothing but pi RSL minus gamma SL minus gamma S times the variation of this quantity, r square sine square theta E. We are writing down the variation of this quantity here, and the variation of this quantity is all the derivatives with respect to r and theta E. So that is 2r dr times sine square theta E plus r square times 2 sine theta E cos theta E times dE d of theta E. That's the first part. And finally variation of the second term would be 2 pi gamma times 2r dr times 1 minus cos theta E. That's the first term. And then note that I am writing down the variation of this term here, plus we have r square times derivative of cosine theta is minus sine theta, so that's plus sine theta E d theta E. That's the variation. Let's give this another label. Let's call this as expression number 2. Okay. Now what we want now is the variation of the energy is equal to 0 at equilibrium. equal to 0 at equilibrium, that is d of E surface of A is 0, right? So what we will now do is we will say dividing both sides by dr, dividing both sides of equation number 2 by dr, we get dE surface by dr is nothing but 2 pi r gamma SL minus gamma S times sine square theta E plus r has been taken out, so they have one more r left, r times sine theta E cos theta E d of theta E. That's what I have. And let me continue this again. We have one more term here, that is 2 pi r is again common, it's outside, gamma times 2 times 1 minus cos theta E plus r sine theta E times d theta E by d capital R, right? And this variation is basically these two brackets. With this whole variation, we'll set it to 0. Okay. Now, we'll first label this. Let's look at what this means. If I say dE by dr is equal to 0, it means that there is no energy variation because of an infinitesimal change in the shape of the droplet. The shape of the droplet can occur either because of change in the radius capital R or the change in the contact angle theta E. So we are saying that in an infinitesimal change in R or theta E does not change the energy of the system at equilibrium, and therefore we have I can now say setting dE by dr so to 0, the drop, rather we can say we can ensure that the drop is at its minimum energy state. Now what about these quantities here? I made one small error here. This should be dE by, correct this, this is dE by dr here, d theta E by dr. Okay, so I'm highlighting them. I have two of these quantities here, d theta E by dr. So what exactly is this quantity? How do I get this? Okay, we want to set this to 0, but how do I get this? So we haven't used one more relationship, which is volume constraint. Now we know that the volume of the drop, let's say call it as V. This quantity is pi r cube by 3 1 minus cos theta E whole square times 2 plus cos theta E. That's the volume of the droplet. So therefore dV, that's the change in the volume. I can follow the exact same analysis that we have done. We are going to differentiate it with respect to r and theta and see what do we get. We want to set this variation to 0. So let's write that down. We have pi by 3 times 3r square dr times 1 minus cos theta E whole square times 2 plus cos theta E. That's the first term. Then I have the next term, which I'll write it here, pi r cube by 3, that is 2 times 1 minus cos theta e times sin theta e d theta e times 2 plus cos theta e. That's the first term. And then I have minus 1 minus cos theta e whole square times sin theta e d theta e. This is the variation, right, of the volume. What we want to do is, we want to set this variation to 0. So I'll make some little bit of space here. We want to set this variation to 0, right? So how do we do this? We can basically set dividing both sides by v by dr, dv by dr, okay, will be pi r square of 1 minus cos of theta e whole square times 2 plus cos theta e plus pi r cube by 3. That's what I have, pi r cube by 3. And we can do some simplification here. We can get 1 minus cos theta outside. In both these terms here, we have 1 minus cos theta and we have a 1 minus cos theta in both these terms. We can pull them out and we can do this, we can simplify the rest of it. And what we now have is, let me just do that. 1 minus cos theta e can be pulled out. We have 2 times 2 plus cos theta e times sin theta e minus sin theta e times 1 minus cos theta e. This whole quantity, maybe I should make a little bit of space for myself here. This quantity multiplying d theta e by d capital R. And this quantity, as we know, is equal to 0. Right? So we can straight away see some simplifications that are possible. Cancellations are possible. If I set this whole quantity to 0, then pi r square will cancel out. I have 2 r's are gone there, and what I'm left now with is 1 minus cos theta e. I can also cancel out 1 cos theta. This quantity will cancel out this with this 1 minus cos theta e. What I'm finally left with is 1 minus cos theta e times 2 plus cos theta e plus r by 3, and we can multiply, we can simplify this a little bit, and what we get is, we get 3 sin theta e plus 3 sin theta e cos theta e of d theta e by dr, and we know this quantity is equal to 0. Okay, so from this we therefore get d theta e by dr is nothing but minus of 1 minus cos theta e 2 plus cos of theta e divided by r sin theta e plus 1 plus cosine of theta e. So by imposing a volume variation in the volume to 0, we have got this d theta e by dr, which is the unknown thing in equation number 3. So let's label this. We have relationship number 4, right? So now we can actually take this is forward. We have substituting d theta e by dr from equation 4 into 3, we get, so it's a little tedious, but let me first write it down. Gamma SL minus gamma S times sine square theta plus r cos theta e sine theta e times d theta by dr. D theta by dr is nothing but minus 1 minus cos theta e times 2 plus cos theta e divided by r sine theta e 1 plus cos theta e. That's the first term in equation number 3. And then the next term would be gamma times 2 into 1 minus cos theta e plus r sine theta e d theta e by dr. So let's write that down, plus gamma times 2 into 2 times cos theta e plus r sine theta e multiplied by so this whole thing we can set it to 0. Now notice that this is a relationship that where only we have the 3 surface energies and the contact angle theta e and r. But if you again pay attention, this r sine theta e will cancel out here. So r has disappeared from the calculation. Disappeared from the analysis that we're doing. So what we now have is, we have the simplification as follows. So we have gamma SL minus gamma S. We have sine square of theta e minus, sorry, I made a small error here. What cancels out is not r cos theta e, what cancels out is r sine theta e. So this is r, this is what I wrote down. So r and sine theta will cancel out. So what now we have is minus cos of theta e times 1 minus cos theta e 2 plus cos theta e divided by 1 plus cos theta e. That's the first term. And then the second term is nothing but gamma times 2 into 1 minus cos theta e minus cos theta e into 2 plus cos theta e by 1 plus cos theta e. This whole thing is equal to 0, right? And so we can do a few simplifications. Multiplying throughout by 1 plus cos theta e, what we now have is gamma SL minus gamma S times 1 plus cos theta e times sine square theta e. So that is sine square theta e plus sine square theta e times cos theta e. That's the first two terms that we have here. Then we have cos theta e times 1 minus cos theta e times 2 plus cos theta e. Then on the second term would just be gamma 1 minus cos theta e times 1 plus cos theta e would just be sine square theta e. That's just 2 sine square theta e minus 1 minus cos theta e times 2 plus cos theta e. This goes to 0. This is what we have, right? We can notice that we can combine a few terms here. Let's combine these terms first. This quantity we can multiply. We can also do the same thing for the last two quantities as well. The last two quantities can also be multiplied. So let's quickly do that. So the multiplication would yield 2 cosine of theta e plus cos square of theta e plus cos cube of theta e. That's the first thing. And then finally here we would have 2 sine square of theta e minus 2 plus cosine of theta e cos square of theta e. This would be 0. Now we can combine a few terms. For example, sine square theta e plus cos square theta becomes 1. We can also combine these two terms. Here cos theta, if I take it common, I get again sine square plus cos square theta. So I'll use that relationship. So gamma SL minus gamma S. The first two things that I've underlined, it's 1, so that's 1. Then I have sine square theta plus cos square theta, that's again 1. So that's again just gives me plus cosine theta. Then I have finally what's left is just 2 cosine of theta e. Over here again we can do a similar I can join a few terms here. The sine square theta e has two terms here. I can combine it with the last one, and therefore what's left is only sine square theta e plus 1 it survives. I have minus 2 plus cosine of theta e. This is 0. And therefore we simply have gamma SL minus gamma S of 1 minus cos of theta e plus gamma of, I have sine square theta minus 1, so that is minus of 1 minus sine square theta plus cosine of theta e is 0. And this further simplifies to plus gamma times cosine of theta e minus cosine square of theta e. If I want to consider a case where cosine of theta is not equal to 1, we simply have gamma SL minus gamma S plus gamma of cosine theta is 0, or we simply have gamma SL plus gamma cosine of theta e is gamma S. Sometimes people also write this to be the cosine of theta e tells me that the relationship between the surface energies, that is gamma S minus gamma SL by gamma, tells me the cosine of the angle. So this equation is referred to as the Young's equation. This is the Young's equation or Young's law. Okay. Now this result that we've got here is valid is valid for a much wider case than what we have just derived here. This is a very fundamental equation in capillarity. So let's quickly recap what we have seen in the lecture today. We started out by considering a partial wetting condition. We took a sessile drop on a surface. We assumed the sessile drop to be part of a spherical cap. We then wrote down the expressions for the volume and the energy of the spherical cap. Then we wrote down the total energy of the system that needs to be minimized. Then we substituted the expressions for the various areas that we have, and therefore we got the energy. We considered a variation of this energy, and we set the variation of this energy to 0, and we got this unknown quantity, which is the variation of the angle with respect to r. We impose the volume constraint now. We said if the volume variation in the volume is 0, which means that the volume is constant, then we can combine the two relationships, and finally we can get the Young's angle. Okay, the Young's angle or the equilibrium angle, cosine of theta e, is just simply related to the various surface energies that are present in the problem. Now, what we have not done so far is to consider a situation where the drop shape is not known. Here we have used the exact shape of the droplet using geometry. What if I don't know the shape of a droplet, or it's not so straightforward? In such cases, we'll have to take a more general approach where we'll have to write down the energy in terms of an unknown height function, the height of the droplet, and then we will have to impose these boundary conditions as well, and then we'll use the Euler-Lagrange equation or the energy minimization on an auxiliary function, where we'll have to invoke the Lagrange multiplier and so on. So that's what we're going to do in the following lectures. So I'll see you around in the next lecture. Thank you.